Say you're me and you're in physics and your teacher is rambling on and on about the magic of energy. So you get to thinking about the nature of energy and what is it anyway and what things have energy and why. The general idea you start to understand is that energy is a property of an object at a particular time like mass. In the same way that mass can be lost or gained like a person on the South Beach diet, yet they stay the same person, so too an object can lose or gain energy without changing its identity. Any energy that is lost from one object does not really disappear but is transferred to another object or series of objects like the environment. Just like how the universe as a whole never loses or gains matter, energy is also conserved. Our conception of energy seems a little odd to us because it is hard to visualize these energy exchanges, since we can't see energy, and because they happen too fast for us to follow mentally. So kinetic energy is any energy due to motion. It can be defined as both the energy needed to get an object to a certain speed and the amount of energy the object is able to impart as a result of its motion. Since work is also defined as an amount of energy, this also means the amount of work needed to change an object's speed or the work the object can do on something else. So how do we find kinetic energy? Let's say you're listening to your iPod and not paying any attention as you cross the street and a car is coming and it's not going to be pretty. You know intuitively that a more massive vehicle can do more damage, the equivalent of doing more work on you, so kinetic energy must depend on the mass of the car. You also know that the car can do more work on you if it's moving faster, so kinetic energy also depends on speed. Kinetic energy is a scalar value. It does not make sense for an object to have direction-dependent energy, but in this relationship we use velocity, which is a vector. By squaring it, we eliminate any negative signs denoting direction of the vector, so it becomes irrelevant that we are using velocity the vector and not speed the scalar. Say hello to my friend the Neanderthal. He's not up to date on his rules of the road, so he's in for a bit of a shock in a second. He is hit by that truck from before and starts moving immediately at 20 meters per second. He's small for a Neanderthal, so he weighs about 70 kilograms. What is his kinetic energy immediately after the collision? So if his kinetic energy is actually twice as much, how fast was he moving immediately after the truck hit him? Okay, enough fooling around. We're in space now and the USS Enterprise is traveling at warp 2 when it collides perfectly elastically with a stationary space creature of unknown origins. Don't worry, everyone's fine. Now because you're me, you know the mass of the Enterprise is 190,000 tons, and you also know the equation for velocity and faster than light travel is the warp factor cubed times the speed of light. The crew of the Enterprise is able to use the main deflector dish to determine the mass of the strange creature, which has seemingly magical qualities but is ultimately explainable by science. Because you're me, your computer falls and you have to tape it back up on the wall in just a second. There you go. The speed of the creature after the collision is 10 to the 11th meters per second. The Enterprise's computer systems are all out of whack after the big collision, so Kirk asked Mr. Spock to determine the ship's new speed using science. In an elastic collision, the energy is conserved, and because the alien was stationary before, Spock knows that the kinetic energy of the Enterprise before the collision is the same as the kinetic energy of the Enterprise and the alien combined after the collision. Mr. Spock is pretty good at mental math, so he can use some quality algebra and unit conversion to determine the new speed of the Enterprise. Spock would not forget to square his variable like I did just there. Though the Enterprise has lost a lot of energy, the warp factor is not that much lower. They are moving much faster than light, remember. And maybe this kinetic energy business doesn't work very well when you're breaking the ultimate speed limit, but for the sake of the problem, let's pretend that it does.